The frequency rating of a circuit breaker indicates the frequency for which it is designed to operate effectively. Using a circuit breaker outside of its intended frequency can affect its performance. Let's explore these effects on heating, interrupting capacity, and continuous ampere rating. Firstly, regarding the heating effect, consider a 60 Hz circuit breaker in a 50 Hz system. The lower frequency reduces inductive reactance, leading to increased current flow. This can result in excessive heating of the circuit breaker's contacts and coil. Conversely, if we use a 50 Hz circuit breaker in the 60 Hz system, the higher frequency increases inductive reactance, which reduces the current flow. However, the reduced current might not be sufficient to trip the circuit breaker promptly during an overcurrent situation. Secondly, let's discuss interrupting capacity. When using a 60 Hz circuit breaker in a 50 Hz system, the lower frequency generally reduces the interrupting capacity. This is because of the decreased inductive reactance. The circuit breaker may not be able to safely interrupt a fault current at 50 Hz. In contrast, using a 50 Hz circuit breaker in a 60 Hz system, the higher frequency increases the interrupting capacity due to increased inductive reactance. However, the circuit breaker may not be able to withstand the higher fault currents present in a 60 Hz system. Thirdly, consider the continuous ampere rating. For a 60 Hz circuit breaker in a 50 Hz system, the lower frequency reduces the heating effect. This allows the circuit breaker to potentially carry a higher continuous current. However, for a 50 Hz circuit breaker in the 60 Hz system, the higher frequency increases the heating effect, reducing the continuous ampere rating of the circuit breaker. In conclusion, using a 60 Hz circuit breaker in a 50 Hz system is generally acceptable. However, it is not recommended to use a 50 Hz circuit breaker in a 60 Hz system. Frequency mismatch can lead to adverse effects, including reduced interrupting capacity, increased heating, and decreased continuous ampere rating. These effects stem from changes in inductive reactance and current flow caused by the frequency difference. It's crucial to select circuit breakers with the correct frequency rating to ensure reliable and safe operation of electrical systems. The inductive reactance, often denoted as X sub L, is directly proportional to the frequency, represented by F, and the inductance, represented by L. The formula is X sub L equals 2 times pi times F times L. In a 60 Hz system, the inductive reactance is higher than in a 50 Hz system, assuming the inductance remains constant. This difference in inductive reactance affects the current flow during normal operation and fault conditions. A higher inductive reactance limits the current, while a lower inductive reactance allows more current to flow. The interrupting capacity of a circuit breaker refers to the maximum fault current that the breaker can safely interrupt without being damaged or causing an arc flash. This rating is determined by testing the circuit breaker under specific conditions, including voltage, frequency, and fault current levels. When a circuit breaker interrupts a fault current, it creates an arc between the separating contacts. The circuit breaker must be able to extinguish this arc quickly and safely to prevent damage to the breaker and surrounding equipment. The interrupting capacity is typically expressed in kiloamps, which is thousands of amps. The continuous ampere rating of a circuit breaker, also known as the current rating, indicates the maximum current that the circuit breaker can carry continuously without exceeding its temperature limits. This rating is determined by the design and construction of the circuit breaker, including the size and material of the conductors, contacts, and insulation. The continuous ampere rating is typically marked on the circuit breaker's nameplate. It is crucial to select a circuit breaker with a continuous ampere rating that is appropriate for the load it will be protecting. Overloading a circuit breaker can cause it to overheat, which can lead to premature failure and potentially create a fire hazard. In a 50 Hz system, a 60 Hz rated circuit breaker might experience reduced heating due to the lower frequency, potentially allowing it to carry a slightly higher continuous current. However, this should not be taken as a license to overload the circuit breaker beyond its rated capacity. The safety margins built into the design of the circuit breaker should always be respected. Furthermore, the reduced interrupting capacity when using a 60 Hz circuit breaker in a 50 Hz system is a significant concern. In the event of a fault, the circuit breaker may not be able to clear the fault current quickly enough, which can lead to equipment damage and potential hazards. It is essential to ensure that the circuit breaker's interrupting capacity is adequate for the fault current levels in the system. Using a 50 Hz circuit breaker in a 60 Hz system is generally not recommended due to the increased heating effect. The higher frequency can cause the circuit breaker to overheat, which can reduce its lifespan and potentially lead to premature failure. Additionally, the reduced continuous ampere rating can limit the amount of current that the circuit breaker can carry safely. The circuit breaker's performance is significantly affected by the frequency of the electrical system. The inductive reactance, heating effect, interrupting capacity, and continuous ampere rating are all influenced by the frequency. It is crucial to select circuit breakers with the correct frequency rating to ensure reliable and safe operation. Always consult with a qualified electrical engineer or electrician to determine the appropriate circuit breakers for your specific application. The choice of circuit breaker should be based on a comprehensive assessment of the electrical system, including voltage, frequency, fault current levels, and load requirements. Regular inspection and maintenance of circuit breakers are also essential to ensure their continued reliable operation. This includes checking for signs of overheating, corrosion, or mechanical damage. Circuit breakers should also be tested periodically to verify their interrupting capacity and other performance parameters. The testing should be performed by qualified personnel using appropriate test equipment. In addition to frequency rating, other factors to consider when selecting circuit breakers include voltage rating, short circuit current rating, and coordination with other protective devices. The voltage rating of the circuit breaker must be equal to or greater than the system voltage. The short circuit current rating must be greater than the maximum fault current that the circuit breaker may be subjected to. Coordination with other protective devices, such as fuses and other circuit breakers, is essential to ensure that the protective devices operate selectively to isolate faults and minimize the impact on the electrical system. Different types of circuit breakers are available for different applications, including miniature circuit breakers, molded case circuit breakers, and air circuit breakers. Miniature circuit breakers are typically used in residential and light commercial applications. Molded case circuit breakers are used in commercial and industrial applications. Air circuit breakers are used in high voltage and high current applications. The selection of the appropriate type of circuit breaker depends on the specific requirements of the application. Consider the specific voltage, current, and frequency requirements of the application. Also, consider the environmental conditions in which the circuit breaker will be installed. Factors such as temperature, humidity, and altitude can affect the performance of the circuit breaker. When replacing a circuit breaker, it is essential to select a replacement that has the same or better ratings and characteristics as the original circuit breaker. The replacement should also be compatible with the existing electrical system. Never replace a circuit breaker with a low-rated breaker, as this can create a safety hazard. The NEC, National Electrical Code, provides detailed requirements for the selection, installation, and maintenance of circuit breakers. The NEC should be consulted to ensure that all electrical work is performed in accordance with applicable codes and standards. Section 240 covers overcurrent protection. Specifically, Article 240.6 dictates the standard ampere ratings for fuses and inverse time circuit breakers. Article 240.83 discusses the marking requirements for circuit breakers, and this includes ampere rating, voltage rating, and interrupting rating. The interrupting rating must be sufficient for the available fault current at the line terminals of the equipment. Consider the importance of proper circuit breaker selection and application for ensuring the safety and reliability of electrical systems. Incorrect circuit breaker selection can have serious consequences, including equipment damage, fire hazards, and even personal injury. Therefore, it is crucial to follow best practices and consult with qualified professionals to ensure that circuit breakers are properly selected and applied. Circuit breakers are designed to protect electrical circuits from overcurrents, which can be caused by short circuits, overloads, or ground faults. When an overcurrent occurs, the circuit breaker trips, interrupting the flow of current and preventing damage to the circuit and connected equipment. Circuit breakers are an essential component of any electrical system, and their proper functioning is critical for ensuring safety and reliability. The internal components of a circuit breaker include contacts, a trip mechanism, and an arc extinguishing system. The contacts are the conducting parts that make and break the electrical circuit. The trip mechanism is responsible for detecting overcurrents and causing the circuit breaker to trip. The arc extinguishing system is designed to quickly and safely extinguish the arc that forms when a circuit breaker interrupts the current. The trip mechanism can be thermal, magnetic, or electronic. Thermal trip mechanisms use a bimetallic strip that bends when heated by an overcurrent, causing the circuit breaker to trip. Magnetic trip mechanisms use an electromagnet that attracts a plunger when an overcurrent occurs, causing the circuit breaker to trip. Electronic trip mechanisms use electronic circuits to detect overcurrents and cause the circuit breaker to trip. Arc extinguishing systems typically use arc chutes or arc runners to divide and cool the arc, making it easier to extinguish. The arc chutes are made of insulating material and are designed to force the arc into a narrow channel where it is cooled and extinguished. Arc runners are metal plates that are positioned near the contacts to attract the arc and move it away from the contacts, making it easier to extinguish. The performance of a circuit breaker is affected by various factors, including temperature, humidity, and altitude. High temperatures can reduce the interrupting capacity of the circuit breaker. High humidity can cause corrosion of the contacts and other components. High altitude can reduce the dielectric strength of the insulation. To ensure the reliable operation of circuit breakers, it is essential to perform regular maintenance, including visual inspection, cleaning, and testing. Visual inspection should be performed to check for signs of damage such as cracks, corrosion, or overheating. Cleaning should be performed to remove dust, dirt, and other contaminants. Testing should be performed to verify the interrupting capacity and other performance parameters. Circuit breakers should be tested using appropriate test equipment, such as a circuit breaker tester. The test equipment should be calibrated regularly to ensure accurate results. If a circuit breaker fails a test, it should be replaced immediately. The lifespan of a circuit breaker depends on various factors, including the number of operations, the severity of the overcurrent, and the environmental conditions. Circuit breakers that are subjected to frequent operations or severe overcurrents will have a shorter lifespan than circuit breakers that are subjected to less frequent operations or less severe overcurrents. Circuit breakers that are installed in harsh environments will also have a shorter lifespan. It is important to replace circuit breakers before they fail to prevent potential safety hazards. The frequency rating of a circuit breaker is an important parameter that should be considered when selecting and applying circuit breakers. The frequency rating affects the inductive reactance, heat effect, interrupting capacity, and continuous ampere rating of the circuit breaker. It is crucial to select circuit breakers with a correct frequency rating to ensure reliable and safe operation. Always consult with a qualified electrical engineer or electrician to determine the appropriate circuit breakers for your specific application. The information provided is intended for general guidance only and should not be considered as a substitute for professional advice. Always consult with a qualified professional before making any decisions related to electrical systems. Understanding the effect of frequency on circuit breakers allows one to be able to determine its appropriate usage.